Okay, so discrete optimization, part 6, last part, okay? And so what I'm going to talk about today is where is this dual coming from and why is it useful, okay? So we saw that it was beautiful, okay? We have no idea, where magically it came from, okay? And so that's what I want to talk about, in this lecture. And then I want to also tell you a little bit what it means, so how you can understand these things, okay? What is the meaning of these dual variables? And then I want to talk about, what is useful for, okay? So this is, understanding where it came from, okay? So this is an example that I took from Lova's book. If you have to read 2 books on linear programming, this has to be one of them, okay? So what you see there is basically a linear program. I'm maximizing my profit here. I'm maximizing this objective function, subject to these constraints, okay? And the question is that, I'm asking, the question, can I bound this maximum? Is there an optimistic evaluation of that maximum, okay? And so what I'm showing you here is one of them. I'm basically telling you here, okay, that the maximum value that this objective function can ever take is 110, okay? Why? Okay, so look at these constraints and look at this one. Look at these 2 constraints, okay? So this is 55, this is 110, okay, double. Why? Because I basically took that constraint and I doubling every one of the coefficient, okay? So instead of having 5, I get 10, okay? Instead of having 1, I get 2. Why did I do that, okay? Because as soon as I do that, okay, so what you can see, okay, is that this 10 here, okay, is actually greater than the coefficient in the objective function. This value also is greater. All the values here are greater than the objective function. And therefore, I'm maximizing something which has to, so if this has a value, this will have a larger value. Okay, the objective function has a value. This has to be greater than the value of the objective function by definition. Okay? And therefore, in this particular case, I know that 110, okay, has to be an upper bound. Okay, I will never be able to get to get higher than 110. Okay, so that's an upper bound. No, this is a terrible upper bound, of course, but I'm going to show you better ones. Okay, so look at these 2 things here. I basically take these 2 constraints, I add them together. Okay, if I add them together, I get these constraints that you see here. Right? So you basically see here 4x1, plus 3x2, and so on, smaller or equal to 58. Okay? So now, once again, you can do the same reasoning. You can look at all the coefficients that you see there, and once again, they are always greater than the coefficients inside the objective function. Okay? So greater or equal, right? So this 4 is the 4 of the objective function. The next one is 3 instead of 1. So I know that if I sum these 2 terms there, they will be smaller than the sum of these 2 terms. I continue doing the same way, right? So the 5 in the objective function becomes 6, okay? And the 3 remains 3, okay? So I know that this value is always going to be greater than the value of the objective function, whatever the value that I find for the variables. But now this time, the value here is 58. So it's a much smaller value. So I know that 58 in this particular case is a bound to this objective value already. Okay? So wow. Okay, so what I'm showing you here is by combining these constraints and by actually making, making sure that these combinations satisfy some basic constraints that have to be greater than the coefficients of the objective function, okay, I can actually bound the value of this objective function, okay? And that's very nice, okay? So in a sense, but what is the relationship with the dual, okay? So look, what I'm going to do is to take an arbitrary combination, positive combination, it's called conic combination, of these constraints, okay? And so if I do that, I'm basically going to use y1, y2, and y3 to find the coefficients of the way I want to combine this equation, right? Hey, think of it, y1, y2, y3, does that remind you of something? Okay, so I'm basically taking this y1, y2, y3, okay? And then I'm basically multiplying the various constraints that you have there, okay? And I know that, when I do this combination, okay, so I have to be smaller or equal to this particular value here. Okay, because these are the right-hand side of these constraints. Okay, so if I multiply this left-hand side by y, I have to be smaller or equal to that. Okay, so I know that if I multiply this constraint by y1, y2, y3, okay, I have to be smaller than this expression here. Okay, and once again, right-hand side, hey, objective function. So if I minimize this, okay, I know that the value of this, because of this combination, has to be greater than the value of has to be greater. I know that these values will have to be greater than this thing, right? But what I want to do is to find the tightest upper bound. So I minimize this. Okay? So I want to find the y's that are basically minimizing the value of this expression that I want to be bounding this thing by above. Okay? Now, I told you before we have to satisfy some constraints, right? So when I look at these coefficients, they multiply them by the y's. I have to make sure that, they are greater than the value of the coefficients in this primal, right? And so in a sense, what are these? Well, these are the dual constraints, okay? So this is the dual objective function. These are the dual constraints, okay? So the whole thing here is just a trick to actually bound the value of this primal, okay? So the dual is basically bounding this value, and that's what I told you before, right? So the other day, what we were doing is the primal might be minimizing, the dual was, maximizing, and basically the dual was always a lower bound to the value of the primal. Here, I'm basically maximizing. Of course, the dual is minimizing, and I'm always telling you, hey, the dual here has always to be an upper bound to the value of the primal, okay? And this is a systematic derivation of why this is true. Of course, once you realize, this is an interesting linear program, you can start what are the properties of this thing, and that's essentially what I've shown you last time, okay? That the objective function of the primal optimality is equal to the objective value of the dual optimality. So this value here that you are minimizing is going to be exactly the optimal value of the primal, okay? So that's how you actually find the derivation, where this dual is coming from, essentially, okay? Now, so you have so I'm going to talk about complementary slackness, and this is essentially starting trying to convey what these dual variables mean, okay? And so in a sense, this is a topic which is, a very interesting topic in mathematical programming in general. This is applied to linear programming only, right? So what you see here, what basically these equations are saying is that if you have x star and y star, solutions to the primal and the dual, you have to have these conditions which are satisfied. And I'm going to go over, over them. But essentially what it means is that if you look at the constraints of the primal, this is a constraint of the primal. It's an inequality, right? And if this inequality of the optimal solution is tight, so it has to be the case that either this inequality at optimality has to be tight, or the dual variable has to be 0. Okay, so this is linking the primal solution, the primal optimal solution, and the dual optimal solution, and basically saying, either that constraint in the primal is tight, or the dual variable is 0. Okay, and this is essentially expressing the same thing from the dual, right? So it's these constraints in the dual is tight, or the primal variable is 0. Okay, very interesting. Okay, very interesting relationship between these things. Okay, so you can guess which values are 0 in the other side, depending upon whether the constraints are tight. Okay. Now let me give you an economic interpretation of this. Okay, so once again, I'm looking at this program, okay, this linear program, and we are maximizing. So think maximizing profit. Now you have constraints. Okay, for instance, the constraint could be production, capacity constraints on your production. Okay, so basically this BI over there, okay, is telling you, this is as much as you can produce. Okay, so basically you want to maximize your profit. This is what you can produce. Okay, but we are limited in what you can produce. Okay, so look at this TI there. So what I'm looking at here is, assume that I can increase my capacity production a tiny bit. Okay, what's going to happen? And this is essentially what these dual variables are telling you. Okay, so if you increase your capacity a little bit, okay, the value of the objective function is going to change tiny, in a tiny fashion. Okay, it's going to still be it's going to still at least be as good as the primal objective function that you see there is z star. Okay, but then you're going to increase it with what? With ti times yi star. Okay, for every one of these dual variables. So which basically means that if I increase the capacity of these various constraints on the capacity, okay, I can increase the value of the objective function by multiplying this increase by the value of the dual variables. Okay, so the dual variable is in a sense telling you how much increasing that particular capacity, relaxing that particular constraints is bringing to the objective function. Okay? Now this is only valid when ti is sufficiently small, right? Because at some point, if you make this ti sufficiently big, you may change basis and so on and so forth. Okay? But this is essentially telling you may change fundamentally the nature of the solution. But here, when you are very close, this is what this is basically telling you. Okay? So one last thing that I have to tell you, duality in the tableau. Okay. So remember, when we presented the tableau, you always start with a basis. Okay. So when you start with a basis, okay, so you know that at the end of the day, when you are at optimal solution, these are the value of the objective function. Okay. Now, when you have the first basis, it's either the artificial variables or a basis that you found after the first phase or something like that. You have this basis and assume that these are, let's say, artificial variables. Okay, the cost of these things is 0 in the objective function. Okay, so what do you know? You know that when you look at this formula, the Cj has to be 0. Okay? You also know that this matrix here, AJ, this is the unique matrix. This is a unit thing. Okay? So essentially, what you have here is that what remains of this is basically the value of these guys. So CB, AB minus 1, which you recognize as the simplex multipliers, right? So in a sense, the cost here, so what you will find in those locations are the simplex multipliers, which are the dual variables. Okay? So essentially what you see there is that if you solve the primal, you can always look inside your tableau and you will find the value of the dual variables. You will find a solution to the dual variables. So not only you know that the dual is a particular cost, but you can actually retrieve the value of the dual variables at optimality. Okay? Now, why is this thing useful? Okay, so we have this beautiful theory. We know where it comes from. We know what it means from an economic standpoint, for instance. But what does it correspond to? Okay, so let's look at this example. Okay, so we have a primal which is feasible. Okay, so the dual is not feasible until you get at optimality. So you start your primal, you start minimizing. The dual at that point is infeasible. Okay, so because essentially, so you have to think, the primal is always feasible and get down to a point. In all these things, the dual is infeasible, and at some point you get to the optimal solution. The dual becomes optimal and at the same time feasible. Okay, so the dual. So when you do the dual simplex, okay, so the dual is always feasible and the primal is not until you reach optimality. Okay, so in a sense, what I'm telling you is that you can solve the primal, and then when at optimality you have a solution to both the primal and the dual, or you can solve the dual, and then at optimality you have a solution to the primal and to the dual. So which one do you do? Okay? Well, there is one case where it's actually very useful to use the dual. Okay? So assume that you optimize the primal. Okay, you optimize that, you have the objective, you have the optimal solution. And then somebody comes and say, ooh, I forgot to tell you I have this one constraint. Okay? And obviously, if the constraint is satisfied, it's not interesting. But assume that the constraint is not satisfied. What's going to happen? Okay? Well, the dual, okay, is going to be feasible. Why? Because if you look at these constraints in the dual, what is it? Oh, you flip, and it's a variable. Okay? So if you add a variable to the dual, of course, the dual is still feasible. You can give a 0 to all these variables, and you have the same solution, right? The primal is not feasible. This constraint is violated. So what you can do is to say, oh, but my dual is feasible, so I can optimize the dual. I get to optimality, and at that point, I know that the primal is going to be feasible. Okay? So in a sense, if I'm adding a constraint to a primal algorithm, okay, and obviously, if this constraint is feasible, I don't have a basic feasible solution to start from in the primal, but I have one in the dual, and I can optimize the dual, get back to optimality, and there I know that the primal is going to be feasible and optimal. Okay? So in a sense, if I have an optimal solution to the primal, I add a constraint and that constraint is violated, I can optimize the dual to get back to optimality and feasibility by using the dual algorithm. Very nice. Okay, you will see why this is very nice in the next couple of lectures when we do mixed integer programming. Okay? Now, the other things that we can do is that actually, you can do primal and dual on exactly the same tableau, right? So remember, we have this primal, basically this primal over there. And basically the dual is what? The dual is taking the objective functions of the primal, okay, and putting it as a right-hand side. Okay, where is my right-hand side? Here, right? So we can do the same thing for the objective function, right? So this is the right-hand side of the primal. It becomes the objective function of the primal, okay? And then you have this big matrix, okay? The only thing that you do, you transpose it, right? And so that's what you have here. These two things are the same, okay? So when you have the primal, assume that I don't see the dual. I don't have this representation of the dual, right? I see only the primal, right? But if I want to see the dual on the primal, what do I have to do? I do this, right? And no, I see the primal, right? So I see the dual, right? So in a sense, I don't need this guy because it's already there, right? It's, it's just, a different way of looking at it. So now look at this. If I do the primal algorithm, the primal simplex, what do? I select an entering variable and then I select a leaving variable. Okay? So that's the primal algorithm. If I look on the other side, what does it mean? Ooh, it would mean that in the dual, I would select a leaving variables and then an entering variable. It's another way of doing it. It's fine, right? Because it's going to do a pivoting operation in exactly the same fashion, okay? And when I do the dual, right, if I select an entering variable in the dual and a leaving variable, and then a leaving variable to the dual, what does it correspond to? Well, the leaving variable of this guy is the entering variable of the primal and vice versa. So these things are the same, okay? If I pivot here, I have the same pivot here. If I pivot there, whoops, I have the pivot here, right? So when I add a new constraint, it's violated, and I'm looking at the dual, what do I do in the dual? I'm selecting a constraint to enter the basis and another constraint to leaving the basis, which basically means that here, I'm also selecting a variable, but this time a primal variable to enter the basis and another variable to leave the basis. So when my constraint is violated in the primal and I look at the dual is basically fine. I'm basically doing a pivot operation here. The same thing happens here. But of course, I never have to use this. I can always use one of the tableau and do all the things. I just have to, turn my head, and then it's fine. Okay? So in a sense, that tells you, and of course you could do some steps in the primal, some step on the dual, and you can do all kinds of beautiful things, right? So using the same tableau, okay? So this is the relationship with this primal and dual, and these things you can exploit, and we will exploit them, and you'll understand more of this when we do mixed integer programming. But the fact that we have these two things is really very useful. Okay, so next time we're going to move to mixed integer programming, okay, which is going to be the third big approach to combinatorial optimization, and it will obviously rely on linear programming. Thank you very much.